And so my hope here, and the title of my talk pushes towards that, is that what I'm going to explain is that there is a new revolution that's taking place in the quantiverse, and that in this new set of developments, both scientific and technological, the weirdness is the point. The things that people get hung up about in terms of what does quantum mechanics mean philosophically actually somehow figure more fully in the modern second quantum revolution. These are pictures of different technologies for quantum computers and entangled particles and so on. As mentioned, I wrote this book about Einstein and the quantum. It's a popular book, very few formulas, aimed for a general audience. And the point of the book was that quantum theory, you know what? I want to thank you guys for inviting me. I did forget to do that. Excuse me. I have this opportunity to speak to you. So first thing to understand is that quantum theory was the culmination of a millennial quest by humankind to understand the atom and the fundamental constituents of nature. So you think this is a 2,000 or more year old project of humankind. Einstein was actually central to the success of this project, despite what you may have heard about God does not play dice and his rejection of the theory. And it was about a 25 to 27 year generational effort centered mainly in Germany. And it unleashed immense technological progress, initially in chemistry, then nuclear physics and technology, then information technology. So if I may slightly correct what I heard from Amber, quantum mechanics has been practical and important for the economy since the 30s or whatever, and really is the basis because it's the theory of the atom, and chemistry is all about atoms and molecules and so on. So it's the basis of a huge amount of physics, chemistry, material science, etc. However, now it's being used in a new way for new technology. Okay, and here I was reviewing it. So we actually had a conference on Helgoland with 300 quantum physicists there, and I got to give a talk about the history of quantum mechanics there. And here we are communing with the rock and the apocryphal story of what happened on Helgoland. But actually, mainly this conference was discussing the present and the future of quantum science. Now, in my book, I wrote this. I chose deliberately to be quite brief on questions such as fundamental indeterminism in nature and entanglement and its weird philosophical implications. This is very much a historical biographical book. And why did I do that? Well, quantum mechanics is pretty hard. This is basic quantum, and this is modern quantum, right? It's really hard. You know, I didn't think I would try to push all of this on my dear readers in my first book. But now I am planning to write a second book. It's going to be harder to write. And the thing that's hard about quantum mechanics is not just the math, but also the concepts. Okay. So why now? Well, something has changed in the quantiverse. And what has changed is that quantum physics has come together with information science, and it has led to new fields that have names like quantum computing, quantum sensing, and quantum control, which were not part of physics when I got my PhD 35 years ago or so. So here's a map of funding for modern quantum science, quantum information science worldwide. 56.7 billion is the estimate for this, and this is national funding. The biggest funders are actually US, Europe, and China, so not surprisingly, we're in a kind of international race there. Here is a list of the major corporations that are investing in new quantum technology, which is almost all the tech corporations in the world. Not all, but quite a few of the famous ones. Not to mention 500 startups, which I didn't have time and didn't try to put on this slide. Here's a list of new quantum centers at American universities. Here's a list of new quantum centers in Europe. Okay, and as we heard, it's last year, the Germans got in very well and made last year the year of quantum science and technology, and not this year, which actually is when Schrödinger published his equation and so on. Okay, and if you want to just crudely look at the landscape historically, there's this 1900 to 1936, and you'll know why I said 36, period, which is formulation and interpretation of the theory. And then there's this long consolidation phase where we're filling in the standard model, you may have heard that term, of the universe, understanding the nucleus and the subnuclear forces, elementary particles, applying it to solids, etc. And this continues, and you might call this normal quantum science. There was a roadmap for a lot of this science when I was a PhD student. The new science, the second revolution, was not mentioned when I was a PhD student, so because it didn't exist. Technology, as I already pointed out, transistors, computers, information technology, lasers, optical fiber, GPS, blah, blah, blah. These are all, relying on quantum mechanics in various ways. Now, in the 80s, there was this kind of radical fringe movement that started to think about quantum mechanics in the language of information. And it was really not clear that anybody cared. I was at IBM as a postdoc in the 80s. Two of the originators, Landauer and Bennett, were there. Nobody was taking this seriously. They were smart, it was fun, but it wasn't important. Well, in 1994, that changed. There was a big breakthrough relating to quantum computing, and suddenly people started to look as quantum effects, and particularly the effects that I'm going to talk about, the weird effects, quantum mechanics, not as obstructing our ability to know about the world, but as enabling it. Okay, so this is a Gestalt shift, and that's why we call it the second quantum revolution. I think it's reasonable to call it that. You might think of it as harnessing the weirdness for the good of science and humankind, quantum technology. Okay, so I'm going to try to explain what's so weird about quantum physics. Why do we end up with this weird view of the world? It's going to be historical, but not in the depth that Arne was really historical. It's mainly pedagogical. Then I'll explain what is quantum information, particularly what is a quantum bit. And the quantum computer, what it can do in principle and why it may be the strangest machine ever built. And then one slide on possible social impacts, but happy to talk about that. Okay, so we've heard a bit about this, 1900 to 1911. I use that for a couple of reasons as a discrete period. Planck, as we've heard about, was discussing heat radiation, but actually in most of his work he was focusing on the vibrations of molecules. He called them resonators, but it was really molecules. And he came up with this formula that he needed to explain the law of heat radiation that we've heard about, and the smallest unit of vibration was then epsilon equals h nu. H is Planck's constant, nu is the frequency, and we are contractually obligated by our union to use Greek symbols from time to time in our work, just like lawyers use Latin. Anyway, and that means that the total energy is going to be some quantized number of quanta nh nu. Okay. So now Einstein was really the only person to take this up seriously in 1905, but I'm going to jump to 1907. It wasn't mentioned very clearly, you might have missed it. So Planck was not willing to talk about quantization of energy as being a law of nature until 1908-9. Okay. So, and he barely wrote any. In fact, he wrote nothing about his breakthrough. He wrote nothing about H till 1906. Okay. So clearly he was not able he wasn't willing to say, well, we've got to change all of of physics because of this thing that I've proposed. And let me just say that the sort of natural assumption was when we finally understand what atoms are, we're going to still use Newtonian physics and Maxwellian electrodynamics, but we're going to learn about new forces. In other words, the natural assumption is everything's like little billiard balls and cannonballs and, charges and we're going to learn what's in the atom, but we're not going to learn a totally new view of the world, which is in the end what happened. So here's the quote then for Einstein, who was willing to say that a revolution is needed. And he says in 1907, "For although one had thought before that the motion of molecules obeys the same laws that hold for the motion of bodies in our macroscopic world, we must now assume that the energy of the elementary structures can only assume the values 0, h nu, 2h nu, etc." So he was the first person to do this. He deserves a lot of credit for getting the revolution started, along with Planck. And I want to point out that this is not a minor change that something could be quantized, that the vibrations, and I have this little analogy that I use, I don't have a nice spring for you, but I have a not very nice pendulum, right? And so the pendulum is also an oscillator. It goes back and forth with some frequency. And the energy in this oscillator depends on how high I lift it and then let it go, right? So it'll have more and more, it'll have more and more kinetic energy if I move it higher and then let it go. So it seems that energy can't be quantized because space is continuous. So obviously I should be able to just have any energy I want. And so this is really a problem. It's not a very technical thing. It's a much more visceral problem than you might think for a physicist. It seems to challenge the continuity of space. Okay. Now earlier Einstein had proposed, somewhat independently of Planck's hypothesis, that light also could behave like a particle. And this was after Maxwell had equations had been totally verified and so on, where we knew light was a wave. We had radio. We knew a lot about light, and we knew it, not light, but electromagnetic radiation and light, which is a form of, light is a form of electromagnetic radiation. And so we knew it was a wave. So for Einstein to suggest this was amazingly prescient and bizarre. And so this already introduced this idea that maybe to understand the microscopic world, we're going to have some duality between waves and particles. Now, quantization is something that happens sort of naturally with waves when they're confined. So if we have a violin string that's tied down, then the longest wavelength we can have is twice the length, half a wavelength, between the points where it's tied down, and then you'll have harmonic overtones as shown here. So this is a very natural thing for waves on a string, for example. And by the way, the frequency is related inversely to the wavelength. So if the wavelength's quantized, then the frequency would be quantized. Okay, so this is the first weird property of quanta, that this wave-particle duality that showed up. Skipping a lot of interesting stuff, a big change happened in 1911 because prior to that, there wasn't a clear idea of what the structure of the atom was. And Rutherford and Geiger, German, Marsden, did these famous experiments where they scattered radioactive particles off a metal foil, and they were very surprised that sometimes they got scattered almost backwards, and that implied that instead of the positive charge that had to be in the nucleus, there had to be, it had to be centered, positive charge that had to be in the atom, because atoms are neutral and they have electrons, then it has to have positive charge. That the positive charge was all in this nucleus that's 1,000 times smaller than the radius of the atom. And this led to this solar system model of the atom, where we thought of the solar system as the atom as being just like the planets orbiting around the sun. Now the electrons are orbiting around the atom. And this gives you a clear classical picture, and you could then try to somehow quantize that, okay? But there's the question of stability, because circulating charges are supposed to radiate, and they didn't radiate in the way that would have been expected. Anyway, Bohr, 2 years later, did indeed quantize the orbits, found a formula for predicting what are the quantized energy of the hydrogen atom, and he found that they're not equally spaced energies the way they are for this vibrator, for the molecular vibrations, that instead they're unequally spaced, and that means that different, when the electron moves from one, moves from one level to another, the energy involved is different. That means nu has to be different according to Planck's relation. So you get ultraviolet light, red light, etc., coming out of the hydrogen atom. Now, Einstein in 1917 took this picture up, and he did an analysis of this to try to understand better Planck's formula for black body radiation. And one of the things he said is, I must assume that if I have an electron, this guy is an electron in an upper level below, let's say this is the lowest energy level, that it just randomly falls down by a process called spontaneous emission. And the precise emission time is completely random. There's no prior cause. Nothing came by and bumped it. It just happens. Okay. So quantum theory, according to Einstein, actually has some kind of intrinsic randomness where you have uncaused events. So this is the second weird thing about quantum mechanics. But he didn't like this, and he wrote to Born and said, this business about causality causes me a lot of trouble. I would be very unhappy to renounce causality completely. So already things are getting weird with quantization, wave-particle duality, and now intrinsic randomness. And I do want to talk something about intrinsic randomness. Okay, so what do I mean by intrinsic randomness? This is very important. Okay, things that we consider random, like of course, Einstein doesn't play dice, nor does God, but I do. So, when I throw this, I'm hoping that, if I throw it many times, it'll kind of equally show all the faces. But in fact, every time I throw it, I can do a kind of Newtonian calculation, and I can figure out, if I have a good mirror and really fast technology, I can figure out what's going to come out. And people have tried to do this, to cheat in various games. Okay, so this is not intrinsic random. It's a complicated dynamics that is deterministic, but that you typically can't follow, and you treat it as random. In quantum mechanics, this randomness is uncaused. There's no causal sequence that tells you what's going to, when this atom is going to emit. You can say on average how long it's going to take. Okay, so now as we've already learned something about Schrödinger, Heisenberg, and Born, I give Born a lot of credit here, in 25 to 27, came up with the description that abandons these Bohr orbits, which is very important, and ended up saying that electrons do not have precise orbits, but exist as clouds of probability. The cloud is described by similar math as macroscopic waves, like sound waves, so we called it a wave function, and we use the symbol psi a lot for it, the Greek letter psi. But an electron in a hydrogen atom is always found to have one of the Bohr energies. Psi1 has energy E1, Psi2 has energy E2. So energy is still quantized in this theory, but quantum particles have an uncertain location when their energy is certain. Okay, so this is the third weird property of quantum mechanics. Basically, when you measure the electron's position to find out where it is, its energy and momentum will no longer be what it was before, and this leads essentially to Heisenberg's uncertainty principle. And the measurement becomes part of the theory and affects the measured object. Okay, so here's a representation of these electron clouds for hydrogen in the second and third energy level, and bright is high probability and white is low probability, I guess, here. Now, an important experiment that, can I use it? That's for me. That occurred in 22 before the big breakthroughs, but it has a lot of significance, was by Otto Stern and Walther Gerlach, actually in Frankfurt. And they were testing something they thought related to Bohr, but we now interpret it differently. And it's based on the property of magnets, that if I have magnets and I push the two north poles together, we find that they repel. And if I push the south pole towards the north pole, we find they attract. Okay, and then if I put it sideways so it's not closer to one or the other, then there's actually no force. Okay, and the idea was that the atoms would have magnetic moment from the electrons. They would be like little magnets, and there was some basis for believing that. And that the magnetic moment of the electron would always point either north or south and not in all directions, like a classical magnet. Okay, and here's the apparatus that they used, where they get a beam of silver atoms that go through this magnet, and the silver atoms have their magnetic moment. And if they were just like classical magnets, then some of them would be this way, some would be that way, some would be all directions in between, and you just get this this blurred line for where the atoms end up. But if it always had to be one of those two, then you would get 2 points or 2 blobs, and that's what they found. So that showed that there was real quantization in space that came from the weird properties of atoms and electrons. Now it gets weirder because, for example, the upper branch of this should all be the ones that had that orientation, and let's call that spin up. Okay, so then if I take that same beam there and I put it through another one of these guys, I don't get 2 spots. I only get that spot because it's only the up ones, and the down ones are here. I got rid of them. Okay. Okay, fine, so I only get 1 spot, that's great. So that means it's really up, right? No, if you rotate the apparatus, so you rotate it so that it's not, pointing up as it is here, but sideways, then according to this picture, I should have no deflection, but instead it splits into 2 beams again. Okay, so this is telling you that there's some sort of potentiality, some kind of weird waiting to be measured behavior of the atoms. So this leads to what's called the quantum superposition principle. I'm doing my best to explain it. So think of the quantum spin or moment, magnetic moment, as an arrow of fixed length whose length and direction can be measured. And there's a quantum state which has definite spin for each direction. So it can be up along the z direction or down. But if I change the direction and I have it pointing up along the x direction, that's a new state, a new quantum state. Okay, so actually now you see that any direction has a different quantum state, and so this thing with only 2 levels actually acts like it has a number of states equal to every point on this sphere, all the different places that this could point. Now, if you measure spin in the z direction and the state happens to be happens to be along the x direction, then it breaks up into 2 beams again, like I said, and you won't get a definite result. If you can measure each one of these magnets, they'll be 50% up, 50% down. We call that state a superposition. Okay, so I'm just writing it as plus, as if you can just add them. That's sort of right. The closer the direction of the definite state is, right, this is the definite state. Every time I measure in this direction, I'll always get the same answer. But if I measure in this direction, I won't get the same answer, but it's closer, so therefore I'll get more up and less down. So that's the weird rules that they play by, and so it's impossible to assume that the measurement just reveals a pre-existing state. And I didn't go in. There's a lot of math that can really make this very rigorous. Say, there's no way to say you're just revealing what was there because then some other thing would go wrong. There's just no way to do that. So it's not possible to predict in all these cases what happens in one measurement, only statistically, what happens over many measurements. Okay. So quantum weirdness so far, micro properties are quantized, not continuous. Measured properties of individual particles are generically random. States must be described by probability, not due to lack of any information that we could have, but it's just fundamentally uncertain, okay? Until we measure them, then they force to become certain, but I want to mention that measurement could be either by the humans, by human design, or by the environment, and we can come back to that if you want to talk about that more. So measurement is not a person in a white coat looking at something. Okay. So the theory can predict the probability of all possible measurements, and then a quantum particle with just two possible quantized values on any measurement still has an infinite number of accessible states through superposition. Philosophically, the micro world is more potentiality than certainty. Events are not strictly causal. Strict causality emerges at the macro scale, and certainty is restored by measurements. Okay, and then you have to worry, is quantum mechanics just about our knowledge of the world? All right? So, and not about the real world. By 1930, however, quantum mechanics was accepted as the theory of matter and energy, and 95 more years of research has been based on really the same foundation. There's been no major contradiction, either internal or experimental, to doubt that this is the right formalism. Okay, so must this be the final theory? Einstein and others thought not. Okay, so first I'm going to just go from spins to quantum bits. So, and then I'll get back to that question of Einstein. Okay, so what is a bit? I think most people learn by now that computers process and we transmit information as ones and zeros. And we can think of that as being just an abstract object, but every bit has to have a physical realization. In a standard computer, it will be a voltage in a transistor, or it will be either a photon or not a photon in some packet on an optical fiber, etc. So you need a physical realization, but classical bits are not really quantized. They're just set up so the two states are so far apart that they very rarely somehow get confused between the two. And classical bits only give information about one property at a time. So this is your classical bit. It's either 1 or 0. It describes some property of the system. Quantum bits, on the other hand, okay, quantum bits, they always give 1 or 0, just like classical bits when you measure, but they often only do it probabilistically depending what you measure. And it has this whole sphere of possibilities which are richer than a classical bit. And this is what we use in modern quantum information technology. It could be a spin, it could be an atom, it could be an artificial atom. For example, the Nobel Prize this past year was given for an artificial atom that was invented partially at Yale by my colleague Michel Devray. Einstein's critique of quantum mechanics can be described in the language of spins or qubits. So I'm going to talk about the qubit language. So now spin down is going to be 0, spin up is going to be 1 in the quantum bit. Okay, so in 1935, Einstein, having moved to America and being at the Institute for Advanced Study, still being very troubled by quantum mechanics, publishes this famous article, Can the quantum mechanical description of physical reality be considered complete? This is big news. There's the headline from the New York Times of the same period. And his answer is no, quantum mechanics isn't complete because of entanglement, verschränkten. So if I have 2 bits now, not just 1, so let me go back, 2 bits, they can interact, and in that interaction, they can become correlated in such a way that either the spin is up in both or down in both. And I'm going to write this in this way. So 1, 1 means both up, 0, 0 means both down, but it's equally the two possibilities. But what can't happen, well, I'll get that. So this is like a pair of magic coins. Okay, so I flip my coin, and it's heads, then the other one has got to be heads. The coin looks random, but then the other one is perfectly correlated, or vice versa. If I get tails, then I also get tails there. So these are now called EPR pairs because of this paper, and each coin individually carries no information. If I measure whether it's heads or tails, it's totally random, 50-50. But if I notice the correlation, it's 100%. Okay. And the entanglement does store information because you know about these two coins that when you flip them, you will never get 0, 1 or 1, 0. So that is information. That's a bit of information. Okay. So entanglement can actually store information. It doesn't have to be in the bits individually. It can be stored in that way. Now, the real problem for Einstein was remote entanglement. So now get these two coins, separate them by, the solar system, the distance of the solar system, and now measure one, the other one far away becomes definite. That language is completely wrong. I can correct it if you want. It's abusive language, but in some sense, once you measure it here, you will know that the other one will be. Okay. So how can a measure in here affect the qubit way over here? Well, Einstein says it can't, and he used to also just say this more kind of colloquially, do you really think the moon isn't there when you aren't looking at it? Okay, and there must be a better theory. So that's what he believed to his death. There was this brilliant theoretical physicist, John Bell, who was at CERN, and he was asking the question, could there even be a theory that Einstein would like? Is that allowed? Okay, and what Bell showed was that no theory that Einstein would like, a theory that Einstein would like, would be a theory where something here makes this heads, something there makes that heads, and they don't talk. Okay, that's called a local hidden variables theory. We don't know the variables. We might eventually figure out what the variables are that make this thing that looks impossible possible. That's what Einstein was hoping for. Okay, but Bell realized that actually we know what quantum mechanics predicts for this kind of measurement, not just when we measure in the same direction. Remember, you can measure in different directions. And quantum mechanics gives us an answer for what you'll get. It won't be perfectly correlated, okay, but quantum mechanics tells you. Now he said, suppose this one was definitely heads, and that one was definitely whatever it is, heads or tails. We measured it. Could any such theory work? Okay, and what he showed mathematically was no, that there's actually some angle between the two directions that you measure where quantum mechanics predicts a higher correlation than any realist theory could do. That's wonderful. I won't try to explain it, but that's the... So if we measure this blue point, Einstein is wrong. You can never get an Einstein-friendly theory. This young man, Alain Aspect, in 1982 said, well, I want to do this experiment. Okay, and there's the result, and it kind of looks like the blue that I have here. And this is a point that violates Bell's inequality, which means that no realist theory could explain this by something like 5 standard deviations. It's a pretty good measurement. So it turns out that now we really know that the world is really this weird, okay? And many more experiments have been done, and the things are sent over optical fiber 1,000 kilometers away, and they do this and so on. So it's not just this 1 or 2 experiments. Okay, and Bell was very disappointed because he thought that Einstein was going to be right. Okay, Meanwhile, it took a long time, but Alain Aspect was awarded the Nobel Prize for this experiment in 2022. Okay, so the quantum summary is that quantum systems can live in this uncertain state, collapses into a specific state when you measure it. It's contradictory to assume it's always in the measured state before you measured it, and qubits can be perfectly correlated and behave individually random but can be entangled, like this. Okay, so we're all good, right? We've learned all the hard, weird stuff about quantum mechanics. Okay, so we've covered the essential weirdness, okay, as best we could. All right, so now we get to the quantum information frames. So this is Mr. Feynman again. He's everywhere. Now he's in Times Square with, on a, I think that's an Apple poster, and it says "Think Different." And actually, he was at a conference at MIT in 1981 where for the first time somebody talked about, can you simulate nature with a new kind of computer, a quantum computer? It's not a Turing machine, not like all the conventional computers, but a machine of a different kind with quantum elements. And nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. By golly, it's a wonderful problem because it doesn't look too easy. So he was right about that. It's not at all easy. Well, now there's this guy I won't mention who said, well, this is obviously a crazy idea. Quantum components will randomly be 1 or 0. You can't even store your bits. Forget about processing in a particular way. You're introducing noise. It's really a terrible idea. Well, of course, that isn't how it turned out. Okay, so maybe quantum weirdness is a feature, not a bug. When we try to actually predict what happens in a more complicated quantum system, like many spins interacting with one another, these problems are too hard for us to calculate, not just with pencil and paper, but with the best supercomputers. There are many problems. Oops. So there are many problems in quantum that we would like to know the answer to, but we can't calculate. We don't know how to do the calculation. And what Feynman was getting at is that if we had a computer that itself was quantum and behaved like these spins, we could just run it like an analog computer and we could solve problems that are unsolvable in the current state of science. But the big surprise was the result that was proved by this guy, Peter Shor, who's an applied mathematician at Bell Labs. Okay. And he knew, and many people knew, that quantum calculations aren't the only exponentially hard problems that we're interested in. In fact, he showed that an ideal quantum computer could solve an important computer science math problem relevant to cryptography, which there are many such problems in finance, cryptography, networking, etc. He showed that an ideal quantum computer could break the standard encryption technology which underlies web browsing and e-commerce on the internet. Okay, oops. So that was quite a shock. Specifically, a quantum computer could break what's called RSA encryption used for e-commerce and browsing. And I was wondering, since this is now 1994, right, it's 30 years-ish ago, maybe that's not true anymore. So I asked Google AI. Google AI says RSA encryption is still extremely prevalent and used on 90% of websites. So this thing that the quantum computer could crack, make insecure, is still being used a lot. And the key component in this encryption protocol is finding the prime factors of large numbers. So you remember prime factors, you take a number and you divide it, you separate it into its factors which have no other factors, right? So in 23 is prime, you can look at it and figure that out. But in general, this is very hard. 23 is okay, it starts to get starts to get hard very fast. Okay, so this is a 2048-bit binary number, which is a 617 decimal number, and this is exactly the type of number they use in RSA encryption. You have to find the prime factors of that, okay? And it only has 2 prime factors, and somebody who created this one found the 2, P and Q, and then multiplied them together to make it prime. Sorry, it's not a prime any, well, we had to find it. It's called semi-prime. And no person on, or computer system on Earth can find them unless somebody hacks and finds out what P and Q are. Okay, so they multiplied P and Q together to get this number. That's easy. Going backwards is exponentially hard. And that can be used for encryption, etc. Okay, so and if you share these factors P and Q, it's very complicated. I'm definitely not going to try to explain it. You can then securely say, oh yeah, that's really you because you know the right P and Q, and I see, oh yeah, that factors it. So that's basically how it works, really crudely. Okay. If you had an ideal quantum computer now, we knew that you could actually crack this. And this got the attention of the military, it obviously got the, the attention of, e-commerce people and so on. Okay, I'm running near the end now. Okay, so the last thing I want to really, I'm near the end. The power, what is it about a quantum computer that makes it so super powerful? This is very crude, but let me just do it. So a conventional computer has about 1 billion bits in its memory, okay? Imagine you had a super small memory with only 300 bits, okay? So if it's 1 billion bits and either one can be, each bit can be either 0 or 1, then that's 2 to the n, or 2 to the billion possible things you could write in that memory. If I had only 300 bits, then it would be 10 to the 91 things you could write. Well, that's a lot of things to write into memory. So, okay. So let's try to just do it, okay? We start with all zeros, and then we put a 1 there, we put a 1 in the second place, and keep going through it. And if we did this once a nanosecond, it would take more than the age of the universe to actually write all those numbers. So you can't do it sequentially. This is something you can't do in any regular computer. Okay, but a quantum computer could do it in less than a second, because all I have to do is and so I don't flip the bit, I change it into a 0 and a 1 in a superposition. Okay, and then I do that to the second 0, I make it a 0 and a 1, and you see I'm getting different combinations now. I have 0, 1, I have 1, 0, I now have 4 combinations. If I just keep doing that, I'll in the end have 10 to the 91 combinations. So I can load in this computer this state that includes all possible combinations in 300 operations, which I can do in less than a millisecond, or maybe a quarter millisecond. So now I haven't said this is useful, but it shows how you might get a lot of power out of a quantum computer, and so on. So it's like the ultimate parallel processor. So after the Shor algorithm was invented, the race was on. We now had this new quantum hardware that could qualitatively change the computational difficulty of a problem. All quantum speed up was proven to derive from superposition and entanglement. The computer must stay quantum at every step in the calculation. It can't kind of stop and read an intermediate result or anything like that, unlike any conventional computer or any other previous technology. So that's where we're doing something totally new. There was nothing like this in any technology before the last 2 decades. At the time of the proposal of Shor, there was no quantum computer. We didn't know how you were going to build it. A quantum computer must use the property which Einstein most disliked about quantum mechanics. This time, the weirdness is the point. And EPR that he made up, these EPR pairs, are a resource. And if you read a textbook, there's EPR here, EPR there, because it's a resource for quantum information, not because it's puzzling or philosophically challenging. And there are other exciting new technologies based on quantum control and sensing, some of which I think we're going to hear about. Okay. And the reason the quantum computer is insanely difficult to build is the following. Okay, so a classical bit, as I said, it's very macro. It's very easy to keep it in one state. It can remain uncorrupted for decades. Quantum bit is some kind of real or artificial atom. And an unprotected qubit that's just living in the air or living, at room temperature here, it's just going to get measured by the environment, measured in quotation marks. Okay. All right, so this phenomenon is called decoherence, and it's because other things are interacting with your qubit, and now you're getting correlations with other things that you don't measure, and that makes it look like it's just classical. That's how we get to the classical world, by this work of decoherence. We can't follow all the quantum correlations. We look at a subsystem, and it looks definite. Okay, and this is why there can't be a real Schrödinger cat, but that's a longer story. So quantum information is very fragile, and you can say, okay, let's shield your qubits from the environment, keep them far apart, super vacuum, super low temperature. That's not enough, because we don't just keep bits, they have to interact. They have to interact, and that interaction means they can mess each other up. So they have to be isolated, then they have to perfectly interact, then they have to be isolated. Again, that's why this is the hardest thing anyone ever tried to build. So we're going to need error correction in our hardware. Here's a picture of some quantum hardware that we have at Yale using state-of-the-art cryogenics. You cool down this complicated thing on the left with this can around it to 1/100 of a degree above absolute zero, which I say usually is colder than interstellar space, but I think I'd rather say it's 10,000 times colder than it was outside today. If that's, maybe that's a little more visceral. Okay, so here's one of the artificial atoms that my colleagues invented. This is another kind of technology that uses ions, and there's other good ones that use other kinds of atoms. And it's making remarkable progress, and they have decent quantum computers with hundreds of qubits now, but they haven't solved some grand challenge problem yet with it. And here's my last slide, but if I'm over, I can skip it. No, I think that's somewhat okay. Okay, so what could a quantum computer do for mankind? Again, we can get Einstein in there. That's Einstein with Fritz Haber. Okay, Haber and Bosch in Germany invented this amazing chemical process where you take nitrogen from the air and you get ammonia, and that was critical both for fertilizer and for explosives, and many people know that that led to the Green Revolution of the 20th century. It's very energy intensive. You need 250 atmospheres of pressure. You have to heat up stuff to 450 centigrade, emits a lot of CO2, and it used 1% of total US energy production in 2017. So this is a huge amount of energy that could be saved if we could somehow do it more efficiently. And there is a factor, a cofactor that exists in soil that bacteria use to actually get nitrogen in soil at room temperature and pressure. This is the name of it there. And if we could understand how it works, maybe we could save all this wasted energy using the Haber-Bosch process. Maybe a quantum computer would be able to do this, because this is too complicated to do with the computers we have now. We don't know, blah, blah, blah. Okay, so that's it. Thank you for your attention.
Oh, right. Thank you. Sorry. And thank you, Doug. This was at least understandable to me enough to formulate some questions. But I'm going to wait and see who else. Yes, sir.
One question. Thank you. Thank you very much for this wonderful catalog of weirdness, which was easy to follow, which is impossible. I seem to have identified at least 3 levels of weirdness here. There's the conceptual weirdness, like imagine superposition, imagine spooky action at a distance.
Yeah.
There's the mathematical weirdness, like quantities that don't commute. That's, if you're high school math, that's horrible. And then there is the weirdness that is actually observable experimentally. And there's the philosophical, conceptual weirdness. Now, in what you told us, there was an interplay between these levels. Like when Einstein says, I have a conceptual problem,
Yeah.
you take a while and Alain Aspect does the experiment. So you said the weirdness is the point now in the second quantum technological revolution. Do you think the interplay between these 3 levels is over? Like, I was thinking of shut up and calculate, the famous
Yes.
sentence that someone
I
said
didn't get
once.
to say that, but
I thought you would, so I want to know where you stand on that.
So just for the audience, after there was a reaction against these philosophical things in physics, and by late 50s, including Feynman was very opposed to anything philosophical, and so that became termed shut up and calculate. And I went to graduate school in the era of shut up and calculate, and was told, even though I knew about EPR and so on, don't ever talk about that. So I lived through that. And it's so ironic that now everybody knows about EPR and everybody's using this terminology. I mean, I think what is great about what has happened is that it was, physicists impeded the progress of physics by banishing these comments. Yeah, exactly. And in my field was condensed matter physics. We didn't even talk about entanglement. We called it correlated systems. And we don't want, it's the same thing, essentially.
It sounds nicer.
Yeah, but it sounds less philosophical when we say correlated. So, the idea that there could be, special power in using these correlated and therefore kind of entangled states, I mean, it just didn't exist. And that's why it's almost a revolution, because it really is a change. And as I mentioned, kind of quick, you could prove that that any quantum computer that didn't have entangled qubits couldn't do better than a classical computer. So it's actually, that's what I find is the most dramatic irony of the whole situation. And then it's also made us think a lot about measurement. And we could talk about it more. I think we understand measurement much better. And a lot of the paradoxes of measurement are just misstated. And I did mention in passing that there can't be a Schrödinger cat. And the reason is that, as I said, interactions measure. Even if I don't turn on my microscope or turn on my human device, if something's in the unprotected environment and it's in a superposition, it's going to get messed up. Okay, it's going to no longer be measurable in that way. And so what would happen with the Schrödinger cat is, the nucleus would decay and would start this process where the poison gas is coming, and that would be the measurement. The measurement's over. The cat's definitely, you don't have to wait to look into the box. If that nucleus decayed and was detected by the cat, then it's over, okay? The cat is too macro to stay in any kind of coherent quantum state. It's not even a well-defined. So this is my pet peeve. I could go on for a long time. Because I was at this Caligine concert and all these brilliant physicists are still talking about this Schrödinger cat. But anyway, okay, enough.
So, back here.
Yeah, thank you very much for your talk. I think it was really grounding to look at the grounding principles of all these topics that we will talk about today and tomorrow. So that was really helpful and nice. My question goes in a bit of a more general philosophical direction. when comparing the first and second quantum revolution, and you talked about both of them, I feel like the first quantum revolution was like made in a more like academic, scientific environment, whereas the second quantum revolution, and you talked about that too, is like something that's going more like in this industry direction with like all these startups and like big companies investing a lot of money into that. And my question is, what do you think of that? Is this like a development you welcome?
I don't think that's much of a difference, because once you had the theory of molecules and atoms, suddenly there was all this chemistry, and maybe we didn't appreciate it was quantum because nobody talked about cats and whatever, but it was quantum, right? And here, you know, obviously with the success of the information revolution, there's this, there could be an even better computer is, you know, exciting concept. And so I think that, you know, I think it's comparable. And if anything, I think despite my enthusiasm, understanding the atom was more important than understanding that you could do something with quantum, you know, correlations that nobody had thought you could do. That's very interesting, and eventually it might have some huge impacts, but it's not nearly as important as really understanding what atoms are and to, you know, predictable levels. That's my take on it.
So I want to try and formulate also a philosophical question a bit differently. You said there can't be a Schrödinger cat because it's too macro. And the difficulty that I have always had with the little bits of quantum theory I've tried to understand is not unsimilar to Einstein's. I have a really hard time giving up causality. I mean, we're talking principle of sufficient reason. This is like so basic to philosophy, or at least to all the kinds of philosophy that I know about, that I cannot wrap my head around it. But you said causality emerges at the macro scale, which I take it is connected with the remark you just made about the Schrödinger's cat. Can you explain how that happens? What's then the relationship between the micro and the macro scale, such that you don't have causality at the one level and you do on the other?
Yeah, I mean, this is a very good and difficult question. And what I would say is that we're beginning to understand it better because of this recent progress, because what you do in a quantum computer, which had not been tried before, is you heroically shield fairly macro objects from the environment perfectly. If you don't do it, your computer doesn't work. Okay, so in the electronic quantum computers, you have a nanovolt or nanoamp current going this way and that way at the same time, which people think of as fairly macro. You know, not, it's something you can measure with a, you know, in a lab. It's not an individual atom. So it seems there's no classical quantum boundary except the practical boundary, that it takes heroic efforts to isolate systems well enough so that they behave quantum mechanically for macroscopic times. That's sort of my what I can say about that.
Can I follow that up with a question that was inspired by the young man who was sitting next to me, namely, if there can't be a Schrödinger cat, can there be two Schrödinger cats?
You mean, well, I need that has to be clarified. What are you asking by two Schrödinger cats? Oh, the whole kind of like branching, like it goes into two different universes. Yeah, I feel like that has no explanatory value at all. So I don't consider it part of science, and I don't see why it would make anybody feel better about the world. I mean, so I'll tell you what people like. They like the idea that there's this, you know, this universe in which their dog didn't die, and that's still going on, or whatever. And Yeah, everybody, we're all mortal and worrying about various things that happened, and wouldn't it be somehow soothing to know that maybe that bad thing didn't happen in another universe? I think it's the whole very kind of simplistic attraction of this branching universes thing, because otherwise it doesn't explain anything.
Thank you. Anyone else? Yes. Just wait for the mic, please.
So, to the question of the young man, I think the answer is actually yes, because probably what he's aiming at is if you have entangled states, then of course you can have randomness on two of the cats, right? And so I think yes, but you have to always formulate your question very well, and that takes hours and hours. So it's very difficult to answer a question when you don't know what the context is.
So what
And
I'm objecting to...
you explained the many worlds.
Yeah.
You
No, what I'm objecting to is that quantum mechanics so far doesn't really talk about a living being.
Oh, yes. Yeah.
All right, and we really don't know. I mean, I challenge some people in some other conferences. Okay, write down the wave function for me. I'm a solid state physics. We write down wave functions of big objects, but we don't describe anything like that's intrinsically interacting with the environment through breathing, through blah blah blah. Okay, because there are only certain properties we can get right. We have to, again, so it's really, I think, just even though famous people seem to think it makes sense, I can't make sense of it.
No, absolutely, I agree that, once we talk about cats, I don't think you can really apply quantum mechanics,
Yeah, so-
but it's a good thought
Yeah,
process.
and
It's
let
fun.
me say something else. Okay, which I should have said. Okay, what people have found is certain things that are pretty macro are naturally well insulated from the uncontrolled environment that typically they're in. And one of those would be the current in a superconductor. Current in a superconductor, which you know what that is, superconductor is something you have to cool it off a lot, and then there's no resistance, and the electrons don't talk to the rest of the world very much at all. And that thing, which is pretty macro, just happens to be the right variable. And another thing that's happening, Marcus Aspelmeyer, I think is here in Germany, is sending big molecules.
It's Arndt. It's Marcus Arndt in Vienna.
Yeah. Well, okay, I got it
Never
right.
mind.
Anyway, he's sending big molecules through slits, molecules that look much too big to treat them as quantum particles, and yet he's seeing interference. And that's because the center of mass degree of freedom of the molecule does decouple well from the environment if you do it in ultra-high vacuum. And so these huge molecules, even with like a kind of tail are actually interfering. So if you have the cleverness to isolate from the environment, things can look more and more quantum. That's one of the things we've learned, I think, in the modern era. Big things can look more quantum.
Yeah, I just want to make a few historical comments. Well, one very recent history, it was not Germany who proposed the year of quantum, but Ghana. Ghana, Africa, where there's a lot of people pushing very hard to basically bring, one guy in particular, Henry Martin, who's basically such a driving force in all of Ghana, to bring basically Ghana to, quantum to Ghana, and he's the proposer of the year of quantum. And then, of course, other countries jumped on the boat, because a lot of people said, were slightly opportunistic, especially in ecosystem building and things like that. I said it has to happen now, not 26. And I would say it should even be later, because the quantum mechanical formalism wasn't complete until von Neumann completed it with all the ingredients like density matrices, collapse postulate, which maybe was not that important to calculate hydrogen energy levels, but in everything which now happens in quantum computing couldn't be done without projection postulate. All the entanglement stuff, so it's such a crucial thing, which I think was appreciated. If you see, for example, now at quantum computing, you got things like measurement-based quantum computing, where all the computation is based on the collapse postulate, like iteratively. I mean, you worked on that, Janet, no? Yeah, you worked a lot on that. Yeah, so it's becoming, and it also gives a very new view on quantum foundations and what is essential in quantum mechanics, and the philosophical questions. The conceptual questions are becoming completely different. So It's not anymore about the measurement problem and the many world stuff. It's completely new and sort of a whole new generation who tries to digest quantum mechanics in a very new perspective. I'm not saying there's a final story at all, but there's clearly a very new dynamics going on there.
So I first, I'm not sure I agree with everything you said. Maybe I didn't hear it that well, but I think it's true that there's a much more productive discussion of modern quantum among philosophers where they know what's going on much more and are contributing because they've put some effort into understanding what's going on. And I'm particularly impressed with Rob Speckens at Perimeter, who seems to have a way to explain remote entanglement without giving up causality. He has some way of saving part of it or something. So I agree that it's restarted this discussion of foundations, okay, and maybe probably in a more productive way, although, well, it remains to be seen.
We're slightly running out of time, but one last question over here.
As an economist, I have problems with the costs and benefits of establishing a structure with quantum computers. Can you explain a little bit the costs and benefits you expect from that? And is investment something which should be profitable and being envisaged, or is it something so high in costs that only some internationally research institutes and universities could afford that?
Yeah, that's a good question. I think that it's people have been trying to do this seriously for 26 years, and it's made a lot of progress. But it is pretty expensive. I put some numbers up there, and there's been disappointing progress in finding other killer applications besides this decoding application, which might not be robust because people could change their codes. So I think there could be a flop, a quantum bubble that will flop, although the physics and the computer itself is kind of an amazing achievement of mankind. But I think I changed my last slide. I used to say, well, only time will tell if it really has a revolutionary effect on the economy and the well-being of mankind. Now, there are talks about medical things, there's talk, and some of it, the quantum sensing is already much cheaper. And so it may turn out that the quantum computer was the big shiny object that Google and so on spent a lot of time on. It didn't really pan out as a moneymaker, but that modern quantum technology, which will, maybe catch disease or improve GPS by a factor of 1 million or whatever, will end up, and that's much cheaper. I might say just very quickly that I have a colleague and friend who's invented a quantum technology for separating isotopes much better than the standard thing called calutron. And there's a huge huge industry for radiopharmaceuticals to treat cancer, where you need these isotopes. And so, it's not nearly as sexy as a quantum computer, but it's already got a market. It's already, So I think the variety of things that are getting the quantum label, I include in that things that use quantum control. The way he does it is he makes the isotope he wants magnetic, and then he can pick it out from all the other the majority isotope. So that's just quantum control. There's nothing nearly as complicated as quantum computing, but nobody did it. And it's a new technology that's quantum control based. So there may be others.
So this still leaves us time for a 20-minute break. May I ask you all to be here in exactly 20 minutes? That makes it 20 to 5. And first, but thank you to Doug Stone for